So can we talk a bit more about the FLRW metric, the Friedmann-Lemaitre-Robertson-Walker metric? So this metric, as far as I understand it, was conceived to describe the observations at the end of the day for a universe, but it makes some assumptions. For example, the universe is isotropic, it's homogeneous. These kinds of assumptions, how do we validate the FLRW metric in our universe? How do we know that this is the correct metric that describes the universe on large scales?
Okay, so this is actually related to some research I've been doing recently. So we'll wind back slightly, right? So the Friedmann-Lemaitre-Robertson-Walker metric wasn't developed to explain observations. Okay, so the starting point for the Friedmann-Lemaitre-Robertson-Walker metric, etc., is asking yourself, how do I write down a space-time structure to describe an entire universe? Okay, and so to work with those equations, you have to do what physicists always have to do, is you have to find simplifications, right? We need to find the spherical cow that gives us the mathematics we can actually work with. So when people say, oh, you need the universe to be homogeneous and isotropic, right? This is the cosmological principle. What people sort of miss when you make that statement is that it's not really about homogeneity and isotropy. That is a consequence. But what you are doing is you're putting symmetries on your structure in space. And physicists love symmetries because, of course, they make our problems easier. If you can identify a symmetry, if I could talk about something as a sphere rather than something shaped like a pear, I'm winning because I've got less things I've got to manipulate when it's a sphere, right? So when you put in homogeneity and isotropy, you are making statements about symmetries in the universe and saying about what geometries can space have for homogeneity and isotropy to sort of hold. And we know that there are only 3 geometries for space, right? That can work in this flat, spherical, or saddle point. And we like that because each of those is easy to work with. So what we have to remember, as you said, is that this was an assumption put in to make the mathematics easier, right? Now, what we know today, of course, is that when we look out into the universe, one thing we can definitely say is that the universe is not homogeneous. In fact, it's quite lumpy. And in fact, there was a bit of a buzz in the news over the Christmas New Year period about this result from David Wiltshire's group in New Zealand about, hey, what if dark energy doesn't exist? And what he says there is that actually it's the lumpiness of the universe where you've got clusters and you've got voids which are empty, that the clock rates are different in these 2 regions. And if it's extreme enough, then maybe it's spoofing dark energy rather than dark energy being there, kind of thing, right? So people are...
So if I may, I wanted to get to dark energy later.
Oh, okay.
And I'm glad that you brought up Timescape. It's a very interesting new paper, and I think maybe we can leave that until the end when we speak about dark energy.
Okay.
I'm sorry to cut you off, but before that,
no. I'm happy to go back to my line of thought. So I was saying about so the thing is that so we know that the universe is not homogeneous, and it might not actually be isotropic either. So there have been some results, especially over the last 4 or 5 years now, about people measuring what's known as the cosmic dipole. So there were there was this discovery of the cosmic microwave background back in the 1960s. Accidental discovery, the leftover fireball from creation, etc. But what was realized is that there is a large-scale structure in the cosmic microwave background such that it's hotter in one direction and cooler in the other direction by 1 part in 1,000. So it's not a huge amount, right? It's definitely there. And so what that's interpreted as is that we are moving through the cosmos at a velocity of around 370 kilometers per second relative to the sort of cosmic fireball, right? So that's what the CMB tells us, that we're moving in a certain direction at this particular speed. And that speed is the motion of the sun, but it's the motion of the sun as it orbits around the Milky Way, as the Milky Way falls towards Andromeda, as the local group moves towards the Virgo cluster. So this is like the residual of all of those motions, so 370 kilometers per second. One of the predictions is that if we are moving at that speed, that it should influence all of our other observations. You can think about it as in special relativity. We know that if you're moving at a certain velocity, things are going to be brighter or fainter, etc. You're going to get Doppler shifts. Not huge amounts, because 370 kilometers per second is slow compared to the speed of light, but it should be there. And in the last 5 years, people have been looking at the influence of this motion on the distribution of galaxies over the sky. So if you think about counting galaxies, then our observations are actually going to be distorted by these special relativistic effects, i.e. some galaxies are going to be boosted a little bit brighter, others going to be a little bit fainter. And there's also this effect called aberration, which means that as you start to get up to relativistic speeds, everything tends to pile up in front of your like vision, right, in the direction of motion. So we should have that effect in our count of densities of galaxies over the sky. But because it's such a small effect, you need hundreds of thousands to millions of galaxies to measure it, and you need them spread over a large part of the sky, and you need to be relatively confident that your survey is not full of like the usual kind of stuff, right? You have to make sure, have I detected an object? Have I classified it as a star when it should be a galaxy, vice versa? We're now getting to the case where we are getting robust measurements, and we are getting a disagreement between the velocity we measure from galaxy surveys, which tends to be of order 800 kilometers per second, as opposed to what we see in the cosmic microwave background, closer to 400 kilometers per second. And so there are options, right? Option number one is that, that the galaxy surveys are messy and we haven't accounted for all the systematics which we are trying to work through. But option two is that maybe the cosmological principle doesn't hold. And what I mean by that is that in the cosmological principle, we would expect to get exactly the same result for the CMB and for galaxy surveys. And the fact that we don't might suggest that galaxies are distributed on scales much bigger than we previously thought, i.e. that the universe is a lot more inhomogeneous than we originally thought. If the universe is a lot more inhomogeneous, then there's no way that Friedman, Robertson, Walker can actually hold at all scales. And so, some the more radical people are calling essentially for cosmology to go back to the drawing board and start again and think about inhomogeneous metrics to describe the universe. So it's on the cards. People are thinking about it. At the moment, the evidence is, maybe this, maybe that. We don't really know. But some people really feel like the weight of evidence is shifting somewhat into us having to consider anisotropic cosmologies. The problem is, of course, is which anisotropic cosmology, because there's a lot of ways of deforming a sphere into something else, right? And that would just be the first step. So yeah, it could either be that we've got it all wrong, or it could be like a time of revolution coming up.
Yeah, that's really interesting.